Welcome. So it's math again. I hope you've had a nice weekend. We'll continue with complex numbers. So let's briefly review complex numbers, and then I'll tackle some exercises for you, and then we'll write a bit more. So the heading for those of you taking notes is complex numbers. What we've seen about complex numbers so far is that you should think of a complex number as a point in space, plotting. So you draw a plane like this, and we no longer call this axis the x-axis. We call it the real axis. And then there's the imaginary axis here, which comes from the English word imaginary, because it's like an invented axis standing perpendicular to the number line. Every point in this plane is now associated with a complex number. So there's a complex number, there's a complex number, there are complex numbers everywhere. If the complex number happens to land on the real axis, we call it a purely real number. If it lands on what we used to call the y-axis, we call it a purely imaginary number. So here lies the purely imaginary, the purely real, but the purely real and the purely imaginary are just special cases of a general complex number.
Writing complex numbers as a set.
And if you then project straight down onto our real axis, so the number that lies here will be what we call the real part of z, and we write it like that. And sometimes I've called the real part of z as a. Similarly, if I project out, and by project I mean if I shine a light this way with a lamp, so that point z casts a shadow onto the imaginary axis, then I get the imaginary part of the complex number z.
And that's what I sometimes call b.
And then we saw last time that a smart way to write a complex number was like this: a plus ib. It turns out that if you define a complex number as an ordered pair AB, we discover that there's a very special, purely imaginary complex number, I.
We saw that last time, defined like this.
0. One means that's the number you land on. If you go 0 out on the real axis, starting at the origin, and go 1 up on the imaginary axis. So somewhere around here lies I, and that number plays a crucial role in complex numbers. So it gets its very own name. So that place, it's the number we call I. And we saw last time that I can be perceived as a 90-degree rotator. And what that means is that anything you multiply by, I will consequently be rotated 90 degrees in the positive direction. And mathematicians call this direction positive, because that's the direction in which the quadrant number grows. So that's why it's called the positive direction. So you can thus write a set of complex numbers like this. You can write it as the real part of z, plus I times the imaginary part of the part. And if you look at what I've written here,
then
the imaginary part of a complex number does not contain I. I is multiplied afterwards. And the way to write a complex number, which I have written here, we call rectangular form. Exactly right. Learn the form. Of course, the simple reason is that when you plot your complex number on the complex plane, it forms a rectangle when you indicate where it is. So we also saw last time that if you draw a line from the origin to the complex number z and measure how long that line is, you get what's known as the modulus of the complex number. So you're basically drawing a new rectangle.
Complex plane here with my real axis and my imaginary axis. So if my complex number is 0.5, then I can place it at 0.5.
And I draw a line from z into the origin, then the length of this. Lean. In a way, you can say how large the number is, but you should think more about how far the number is from the origin. The modulus is written with 2 vertical lines. We also believe we'll see that again. So it's modulus z. And if you want to find modulus z, you can use Pythagoras on this right-angled triangle, because here was the number a, and this distance corresponds to the number b. This means we can use Pythagoras such that modulus to z squared is equal to a squared plus b squared. And this means that if we want to find modulus z, we can just take the square root on both sides. So there's this phenomenon. Modulus is a complex number. We also saw last time that there's something called complex conjugate, and it's just a good idea. It sounds complicated, but isn't. It simply means reflected across the x-axis.
So if you have here, again,
the complex plane, and you have some complex number z, for example, here, you can mirror the position corresponding to z over the real axis, and then you end up with a new complex number located here, and we call this number z conjugate. So you can imagine that if this angle is θ, then it's this angle minus θ. So θ is here, and minus θ is here. So it's just a reflection. And you can also imagine if the set of complex numbers is called a plus I times b, so this would be A, and up here would be B. Well, if we mirror this position around the real axis, then down here it would be minus B.
and or on a true hand, be good.
And that means the set conjugate is going to be called A minus IB.
And then there was once a crazy mathematician.
Imagine what you get when you multiply a set of complex numbers by its conjugate. Then he discovered what I'm writing now. He discovered if you take a set of complex numbers and multiply by its conjugate, you get A plus IB. And this is another way to write the set. And it needs to be multiplied by the set conjugate. So I multiply them by diab.
So here it says, if that's z, then this is z conjugate here.
We see the total sum.
Multiply the same two numbers forward style. And then we just think back to,
in high school, we learned that the total sometimes, the same total difference is the square of the first term minus the square of the second term. So this can also be written as the first number squared.
that's what we
The
call
square of the
pursuit.
first term and then minus the square of the second term. But the second term is called IB. So I need to write minus IB in parentheses, then squared. And we can work on this a bit more because a product squared is each factor squared. So down here, it becomes I squared, B squared. So actually it will read a squared minus I squared, B squared. But something absolutely central we saw last time about the number I, which is here, is if you take the number 0.1 and multiply it by itself. So calculate I squared, you get minus 1. And we better emphasize this because it's probably the most important discovery of all in complex numbers that I squared is minus 1. And that means here it actually is minus 1.
So it ends up in the hand.
Minus ones.
But Ian,
Minus times minus, that's
we
plus.
get A again plus B again.
And then the brain thinks a squared plus b squared. This was seen recently. I saw it here. Apparently it's the same as the target.
Well squared.
So this is the same as model use. The end.
And this means that if you want to connect the distance from the origin to a complex number, you just have to take z and multiply it by the conjugate of z, calculate that number, and then square it. And then you found modulus z. So this maybe deserves a little box too, that z times the conjugate of z is modulus z squared. Rec. So we also saw last time that there's something called the reciprocal element. And reciprocal means if you have, for example, the number 5, you can multiply it by the reciprocal of the number 5, and it becomes 1 over 5.
And if you do that, you get the number 1.
And in general, you can say that if you take a real number x and multiply it by its own reciprocal, you get 1. So in the same way, there's a real reciprocal element for all numbers that are not 0. Why not 0? There's no reciprocal number for 0, because you can't say 0 times 1 over 0 and then get 1, because 1 over 0 is not defined. You must not divide by 0. I don't know if you've thought about why you can't divide by 0, but it's obviously because trying to divide by 0 is like attempting to answer an unspeakably silly question.
Well heard every time. Quite a lot of times.
Then there's what's there many times over.
How many times do you earn $0?
Before you earn $100. If you go to work every day and every time you get paid $0, well, it's a long wait to save up $100. How long? It's an incredibly tricky question, right? If anything, it's an infinitely long wait. So trying to answer this question would be like isolating x, right? And if I attempted to isolate x in this foolish question, it would say x must be 100.
I'd use 0 because we're asking how many times 0 goes into 100.
And you can't, can you? So you can divide by something close to 0, but you can't divide by 0 itself. That's why all real numbers that aren't 0 have a reciprocal, but exactly 0 doesn't. In the same way,
All complex numbers that aren't 0 do.
they have a reciprocal. This means the entire Gaussian plane is filled with numbers. And if we just express what was said yesterday and say, we can't consider it. So there's a reciprocal complex number for every number in the whole Gaussian plane. And you might think of it this way. The complex element for number z. It's a reciprocal element to the complex number z. Is it a number that's multiplied by z? We give 1. And we saw last time that if you wanted to find that 1 over z, you could do something smart. So now we want to find 1 over z. And how do we do that? Well, we said 1 over z must be the same as 1 over z if I just extend with z conjugate in both the numerator and denominator. And this is the same as z conjugate, because 1 times z conjugate gives z conjugate itself, because 1 is the neutral element when you multiply with it. Anything multiplied by 1 becomes itself. And down here in the denominator it says z times z conjugate, but we just showed that it was the modulus z squared.
And this number here, it's purely real.
There's nothing complex about this, because all it means is how far is it from the origin out to the number squared? That's what it means. So it's purely real. And therefore, if you use what I've written here, you can calculate this and split it into something that's purely real plus deal with something that's purely imaginary. And we can go over it again. So we get a recap. But the formula looks like this. If you need to find the reciprocal of z, you just need to take the conjugate of z and divide it by the modulus of c squared. That's the formula. That's how you do it.
And an example could be this.
Let's take a complex number z, which is 2 plus 6i, and let's see if we can find its reciprocal. So what's 1 over z? Well, we start with the conjugate of this for the formula, which must be 2 minus 6i. Then we divide by the modulus squared, i.e. I must take this squared plus that squared.
2 squared plus 6 squared.
So we can calculate a bit further. Up here it's still 2 to 6i, and down here it's 4 plus 36, which is 40. And now we can see, as we predicted, the denominator is purely real, which means this fraction can now be split into 2 fractions. So it can be written as 2 divided by 40, which is 1/20th.
Minus 6 divided by 40, which is minus 23 part. Can you do it?
And
That's it.
That's the answer.
So we can see it sounds
That's
silly.
what it says here. That corresponds to the number I had decided to call alpha up here.
And the number here, including the minus, is my beta. And now we found that cyproc element. And what does that mean? It means if you just gather courage, then
And the times of this number I got here, 1/20th minus 3/20ths
it's
in
a
I.
complex number. If I multiply it by the number 2 plus 6i, then hopefully I'll get the number.
Otherwise, it's not that Vesipak element.
So that was board number 1.
Have
for
a good
today.
day.
With a little repetition. Does anyone have questions? That I raised to the power of 2 equals minus 1.
Yes. You can see it. If I draw a picture here, we can look similar.
If you have the real axis here and the imaginary axis here,
And then we take the number 1.
what happens if we multiply 1 by I? No. Well, we've learned that when you multiply by I, you rotate 90 degrees. So if you multiply 1 by I, you rotate up here, and it becomes I. Let's try to take I and multiply by I again. But then I need to take that point and rotate 90 degrees, because now I've multiplied by I again. And if I rotate that place 90 degrees, I end up down here at -1.
So you can visualize this as rotations.
And that's why I started by saying there are two ways to think about numbers. One is as a location, and the other is as a geometric operation. Because when you think about the number I, you need to consider two things at once. You must think of this place as I, but also as something that rotates 90 degrees, but only when you multiply with it. So I is a rotator, and I is a location. Both things are true, and it's good to remember both truths simultaneously when thinking about complex numbers. Do you have any other questions?
Okay, let's jump to board 2.
I feel like it's a nice day today because somehow it's not as hard to get shot today for some reason.
Last time we also saw that you can divide complex numbers by each other. I just want to go over that again because it's important. So we have a subheading for complex numbers called division. And if you have two complex numbers, for example, 4 minus 3i, and you want to divide it by 2 plus I, then it turns out to be smart to multiply the fraction by the complex conjugate of the denominator. Why do you do that? Because then the denominator becomes purely real, and you can split the fraction into two parts, where one is the real part and the other is the imaginary part. So we can rewrite this as open parenthesis 4 minus 3i multiplied by parenthesis 2 minus I, where 2 minus I is the complex conjugate of 2 plus I. And if we do this in the numerator, we must also do it in the denominator. So here we have 2 plus I times 2 minus I. And now we have this situation where we have the sum of products multiplied by the same total difference. And this can be solved mentally, giving us in the denominator down here, we get it squared minus it squared. So 4 minus minus 1, but minus minus 1 is plus 1 because I squared is minus 1. So the only thing to remember when dealing with complex numbers is that you need to know algebra and you need to know that I squared is minus 1.
But there's still plenty of chances to make a mistake.
And up here in the numerator, I multiply this one first, giving 8.
So I choose to multiply this one by that. Why? Because it also gives something real. Because minus times minus gives plus. So minus 3i times minus I gives plus 3i squared. But I squared is minus 1. So it gives minus 3i. You need to keep track of the signs. So I start by looking at the signs and say, okay, minus times minus is plus. I squared is minus 1. And so it must be minus. Then look at the numbers. 3 times 1, which is 3 times 1i, gives 3. Then we say this times that, which is minus 4i. So we write minus 4i. And then we say this times that, which is minus 6i.
And we'll make sure to do it little by little over time.
So colorful.
and
It's
failed
spot on.
away.
Let's try to see what we get. Here we get 5. Here I get minus 10. And it all has to be divided by 5.
Wow, that was
Good
finally.
thing I thought of that.
Let's try to set it up correctly. 5 over 5.
Which I honestly,
That wasn't
I
good.
wish I could say what you mean.
I just had the breakthrough. I'm not doing it.
and then minus 10 over 5, that's minus 2. So that's the answer.
So when you're dealing with complex numbers,
The important thing I asked
pause
is
and
extend
think,
together.
what have I actually done?
Because if you just calculated it, then you're just a chicken, a trained chicken that just does what it's told. But you need to pause and think, what kind of number is this? 1 minus 2i. That's the complex number that, when multiplied by 2 plus I, gives 4 minus 3i.
We're
Every time you
getting
stop and think
better
about it,
and better
then-
friends with the fraction phenomenon.
It makes all sorts of fraction calculations easier to understand. If every time you think, what is a fraction again? All right, a fraction is the number you must multiply the denominator by to get the numerator. That's what a fraction is. It's actually an advanced multiplication.
Multiplication shown here. Please find me something
is
when
multiplied,
he
by
gives
the
the
denominator?
numerator.
That's what's written on the wall.
It's just that repetition is the most important thing.
And I don't know if anyone has any questions. After that, I'm thinking of solving a couple of the exercises I've assigned you. Does anyone have them right in front of them? Or should I try to dig them up? Okay, then
Here's a problem I've come up with. And it looks like I have a set of complex numbers one.
Which is called 4 minus 4i.
And I have another complex number. I've decided to call it C2.
Which is called 4 plus 3i.
and I have to determine, let's just take one of them, unfortunately. 3 times Z1 minus Z2. 3 times Z1 minus Z2. So here we're just calculating exactly as if it were algebra. We say 3 times that number,
Which is called 4 minus 4i.
and then minus that number, minus Z2. But it's important to use parentheses, because Z2, written in rectangular form here, it has 2 terms. And if you don't use the parentheses, you will get a sign error. And let's see, when I multiply that with that, I get minus 12. And when I multiply that with that, I get minus 12i. And when I remove the minus parameter, I say minus 1 times minus 5, that is plus 5. And minus 1 times 3i, that is minus 3i. And then we can reduce it a bit.
Minus 12 plus 5, that is minus.
And sleep. And minus 12i, minus 3i, that must be minus 15i. And then we have the answer. So we can see that when we came up with writing complex numbers, correct Angularfont. Like what? Like a real number plus a real number times I. That's what rectangular font means. Then we can work with complex numbers using exactly the same methods we've used to learn algebra. With the one extra thing you need to know, I squared is minus 1. So I would maybe like to solve problem 5 and 6 and 7 and 8, because in problem 5, I've said, can you calculate I to the power of 3? It's not that bad, right? Because we know what I represents. So this can be written as I squared times I. But I is minus 1, so it must be minus 1i or just minus I.
So that was problem 5.
So it was okay to say. There, you have to determine in the corner. And you can do something smart there, because you can discover that if you take I to the power of 4, what does that
We
give?
can discover that over here to the 4th.
Well, it must be I to the 3rd power. And I to the 3rd is just negative I. So here it stands, negative E times I. But I squared is minus 1, so that gives us negative 1. Negative 1, so it's 1. So I to the 4th, we like that because I to the 4th gives 1. And therefore, it's smart to rewrite this as I to the power of 4. We know we can multiply the exponents. So 2 times 4 is 8. So I've just written the same again. But I know I to the 4th is exactly 1.
Look, it just says
Raised to the
1.
power of 2. So it's 1 itself. And by doing this, we can calculate I raised to all sorts of scary exponents. And in problem 7, you need to be a bit more creative, because you're supposed to calculate I raised to the exponent 104. Of course, you can just start from the beginning. I times I is minus 1, times I is minus I, times I again is 1, and so on. But it's a long way to go until you reach 104. So the trick here is to think, can't I rewrite this into something smarter? Write it as I raised to the power of 4. Because I know what that gives. It gives 1 and 4 times.
What does it get? It's 80 plus 24, so it's 204, right? So the 104 can be written as 4 times 26.
Amen.
So I can write it like this. I raised I to the 4th power to the power of 26, because we know you multiply the exponents. And I to the 4th, I know gives me I. So it actually stands up
Just
there
take the number 1 and multiply it by itself.
26 times. Well, then it still works.
And if something I had said, raised to the 105th, right?
So I've done the same, just added 1 here at the end. So if I were to multiply by I one more time, it would have given I.
So that way, you can indeed calculate raising to all sorts of tricky exponents by getting a bit creative with the exponents.
So finally, now it's gone dark, or not dark, but blurred in problem 8. I asked if one could determine which was larger.
I've written, can it be determined if I is larger than 1?
Or if there's one that's larger than I. Because the normally thinking being would think, well, either that's true or that's true, but there could also be an extra possibility that neither is true. Maybe you can't even order complex numbers by size. And it turns out that the third possibility is the correct one when it comes to complex numbers. You can't order complex numbers by size. Why not? Well, because the idea is that I was larger than 1.
If that's right, then what? Then I should be
I
able
could do what I
to-
usually can do in an option. And what you usually can do in an option is that you can multiply, and you can divide, and you can add and subtract. But I don't know if you remember that when you have an option with real numbers, like this.
Let's start with something we know is true. 5 is definitely greater than 3.
Can I just multiply both sides of the inequality by 2, and it'll still be true? Let's try. Is it true that 10 is greater than 6? Yes, that's correct. So you can do that. You can multiply by a positive number. You try to multiply by a negative number, multiply by -1, for example. Is this what you've said?
So if I multiply by a negative number, remember to reverse the inequality sign.
We knew that from real numbers. So let's assume it works the way we're used to. You can multiply and you can divide. But remember that if you multiply or divide by a negative number, the inequality sign needs to be reversed.
So we could try multiplying by I on both sides here.
If we multiply by I on both sides of this inequality, then it says I squared. As it stands here, it should then be greater than I.
But again, what is that now? That is -1.
Now it says that minus E is greater than I, but here it appears that I is greater than 1. And if you draw the number line, you can see it's nonsense. It can't both be true that I is a number greater than 1 and at the same time say that I is a number less than -1, because what is up here? If I draw it, it's 0, and this here is 1. So the only thing we know about I up here, assuming this is true, is that I lies to the right of 1. If you look down here, it says that I is supposed to be less than -1.
So down here, it's saying I lies to the left of -1.
And obviously you can't have a number that is here and here at the same time. Besides, we also know that
That's
you
right.
are somewhere.
It's right there.
So the answer is you simply can't arrange the complex numbers.
Magnitude, you must give up on that. But you can certainly ask how far a complex number is from the origin, and we call that the modulus of the complex number. Now we'll take a short
10
break from
minutes,
learning something
And then we
new.
resume.
So let's start the new post-break session. Yeah, I hope it's a good break. Here we come to board number 3. The first thing I want to show you is that if you multiply by the imaginary unit, you rotate what you're multiplying it with by 90 degrees in the positive direction. And maybe some of you here can remember having done 2-dimensional vector calculus. How many here can remember doing 2-dimensional vector calculus? Okay, so there might be some of you who have never done vector calculus, perhaps. But you can actually compare the complex number a bit with 2D vectors, and you can think of it as a 2-dimensional vector with an extra rule of operation, actually. But what exactly is a vector?
Well, if I have a coordinate system here,
With an x and a y-axis, then you can draw a 2-dimensional vector representative. So this is a 2-dimensional vector. It's called a representative of a vector because it's a vector with coordinates a over b that I just come up with.
And that vector, I'll just call it V for vector.
And then we've learned that a vector is written using its coordinates, which are placed directly underneath each other, a and b. That's how we write a vector.
And now there
What
was
happens
a
if I just take a vector and rotate it 90 degrees around the origin? So I imagine it's hinged here in the vector. So here's a ball bearing, and here's my arrow. And then I rotate the arrow around the ball, bearing 90 degrees. And if I do that, I'll just try to remove the b.
then I should get something that looks approximately like about like this. Here, imagine it's 90 degrees. And this number here, that was B. And what you can see now, hopefully, on my drawing, is that what used to be A, which was here, the first coordinate, now corresponds exactly to the distance here. But it's just negative because I've ended up in the negative part of the x-axis. And the distance here, haven't I been able to calculate it? Oh, no, I haven't. And because I haven't drawn it well enough, let me just try to draw it here so it's a bit more sideways. I think then you'll be able to see it like this. Let's try to draw it like this. Then I don't think I can draw it so wrong. So here's my vector v. And it has an x coordinate here, which is A, and a y coordinate here, which is B. Take care. And then I rotate it 90 degrees. If I have to try drawing again, something like that. Now, I hope I'm not fooling myself when I look at my drawing. The distance from here to there and the long distance is now here because it's rotated 90 degrees. So what was the x coordinate is now the y coordinate. So here is A. And B, which was here before, is now here, but has changed sign because it ended up on the negative part of the x-axis. So here is minus B. And this new vector has been rotated 90 degrees. They've given it a name. They call it the transverse vector and put a hat on it. Some just call it the hat vector. So the hat vector v hat, what coordinates does it have? So what is its x coordinate and what is its y coordinate? Well, we can see it here. Its x coordinate is minus b and its y coordinate is a. So I can write like this, minus b. So what do I know about this vector and that vector being perpendicular to each other? That's how I came up with it. I just imagined that I took vector v, rotated it 90 degrees, and then I got v hat. You can do exactly the same with complex numbers, and we'll see that multiplying by the imaginary unit does exactly that with the coordinates. So let's now try to imagine that we quickly jump into the story of complex numbers. So here is the real axis, and here is the imaginary axis.
And here is some kind of complex number set. And it's called A plus IB.
So C equals a plus I times B. And now we can see what happens if I take C and multiply it by I, the imaginary unit. Because if I say I times a Z, then I get I times a plus EB. And I can just multiply I into the parentheses.
For I times,
I'll just write that here at the end. And then I get A times I times B. That's I squared B. And I squared is minus 1. So I get minus B. And now you can see that the complex number I get here is called minus B plus B. I times it corresponds exactly to a vector with the first coordinate minus B, as shown there, and the second coordinate A, as shown there. So you can see, multiplying by the imaginary unit corresponds to taking a vector and turning it into its own perpendicular vector, which is equivalent to a 90-degree rotation. So if I were to draw this new complex number here, I'd attempt and rotate this line 90 degrees. It maybe looks kind of like this, so it wouldn't be roughly here.
So this is in the z direction, and that is z.
And here I have rotated 90 degrees.
So minus B, that's the case here.
Oh, wow. That went well.
I hope so. So this corresponds to some vector calculation. What we're doing here, we've already learned in vector math about a unit vector, which is a 90-degree rotated vector. The next thing I'd like to show is about finding what we call the argument of a complex number. So now there comes a subtitle to the title, complex numbers, which is called argument. And we now have to imagine again that we're drawing the complex plane. And if you prefer, you can also call it the Gauss plane. So here is the real axis and the imaginary axis. And here is some complex number z. And we've seen that you can tell where z is by stating the real part and the imaginary part. And if you do that, you're saying you've specified z.
By giving the complex number in its algebraic form.
But you can also tell your neighbor in another way where the complex number z is. You can actually tell your neighbor how far it is out
And
there.
at what angle it is rotated.
And if you do that, you say you've specified the number in polar form. If I maybe
Measure
just...
how far it is out first.
So we know that's what we call modulus, the distance to z, like that. But it's often called r, for radius as well, that number, because it's just a real number. Because then you can think of it as, here is a complex number that lies on a circle with a given radius. And the circle's center is always at the origin. And then you can specify the angle up there to the connection line, measured down from the positive part of the real axis. And I could now call that angle theta. And theta is called an argument of the complex number. So C to R, an argument. And say, and there's a good reason I say an argument and not the argument. The argument is what Danish teachers call the definite form. It's something unmistakable, but that's not the case here. This is just one of infinitely many possible arguments for z. What do I mean by that? Well, if I want to tell my neighbor where z is located, I can tell him how much this line is tilted upwards. But I could also choose to tell him it's tilted upwards at this angle here. Or sway around. And so, or this angle.
All the way around. Let's do it one more time. And then we turn it
And
up.
I can land in that spot. It's not more exact than what you call an integer multiple of 2 pi. And an integer multiple of 2p means an integer multiplied by the value of 2 pi. And what is 2 pi? It's a full circle. So you could say you've turned up 30 degrees, or a full circle plus 30 degrees, or 2 full circles and 30 degrees. You see, there are infinitely many ways to indicate the rotation up to z, but there's only one way to tell exactly how far. So the modulus is completely determined once calculated, but the argument is only determined as accurately as up to an integer multiple of 2 pi.
So how do you find one argument from C? And are there some arguments we can find more easily?
Can we find others? The answer to the last question is yes. There are arguments we prefer over others. In fact, there's something called the principal argument of a complex number. So how do you find one argument? Let's start with that. How do you find that angle? And for that, you just have to imagine drawing the line from O echo to C, and then you draw a triangle here. And here is 90 degrees. And now I imagine myself lying in the first quadrant with my complex number. So if I'm in the first quadrant, the situation looks like this. My z is somewhere over here in the first quadrant. Here's the second quadrant. Here's the third quadrant. Here's the fourth quadrant. So right now I'm focusing on the possibility that z is in the first quadrant. And then at that distance here, I'm exactly matching B, namely the imaginary part of the complex number C. C is here. This down here, that's the origin. So we just rate an O for the origin. And here is the real part of Z. And here is the angle I'd like to find. And if you can remember a bit of math from B level, then you can recall how to find an angle if you know the opposite side and the adjacent side. You need to use something called tangent. And it holds that tangent to the angle theta
Equals opposite divided by the hypotenuse.
the protruding cathode. This will lead to adjusting the cathode. And on my drawing, it will be called B divided by A. And if you want to find the angle, just get rid of the tangent, and you do it by
Taking the inverse
a
function.
function for tangent called arctangent, or tangent inverse, as some also call it. So we now have a formula. You can find one argument for a complex number, one of the infinitely many possible ones. If I say tangent E minus,
It's firm.
Bareback.
let's continue with it. And the thought to my first, that's also what's called Arcus
The long
tangents, which
calculator calls
it
it
says
that.
ACAN. I'll just write out here in parentheses. Sometimes you see tangents minus first
No,
as,
I see.
some calculators call it ARCTAN.
Which is shortened to the word arctan, which basically means inverse.
Inverse thoughts. So you can use this formula to find an argument for a complex number if you know B and if you know R, and we can try that out.
Example. So you can see
It's
it.
relatively simple. Okay, let's talk about the complex number, specifically called 2 plus 3i. If it's in the first quadrant, that's good because the real part is positive, the imaginary part is positive, so it clearly sits in the first quadrant. And it's always a good idea, whenever you need to calculate an argument, to make a drawing. Just to be thorough, because you'll see it's not always as simple as what I'm doing now. So always make a little drawing. I'll just make a quick drawing here. With my real axis and my imaginary axis. And then I have 2 plus 3i. So I move 2 along the real axis, and then I go up 3. And the complex number that's now in the corner of this rectangle, that's my set of complex numbers. They're C. And what I'm trying to find is the angle formed between the line connecting the origin to Z and the positive part of the real axis. That's the angle we're looking for.
That's here. So that's my theta.
And then it's just about plugging it into the formula. And remember to set your calculator to degrees if you want degrees, and to radians if you want radians.
So that means one argument.
An argument for the complex number set. And by the way, it's also written like this: A, R, G, Z.
And we read it. Here is an argument for Z.
Are you following me?
Attention to the power of -1.
Seriously?
3, it will have a 2.
And I can't remember what it gives. Maybe it gives 53.13 degrees. 56, 56.3, 56.3.
So I write approximately equal to, and then I submit just with 3 significant figures. So that's the argument. And just for fun, you could also calculate the modulus of this complex number set, because then I can just tell you a little more. The modulus of this complex number set, it simply means what is the radius of the circle centered at the origin, which contains the set. So you can write the modulus C as R, and we have learned that you just need to take the square root A,
Real part squared plus imaginary part squared, so 2 squared.
you stretch in the brain,
And that gives the square root of 4 plus 9.
that's 13, so I can hear it's 13. And of course you could convert that into a decimal, but we actually prefer to present it as the square of 13, because that's exactly correct. And now you can actually write the complex number set in a new way. And this new way is called polar form.
So the complex number set known as 2 plus 3i is right here. It's called 2 plus 3i. Why?
The reason is you should be able to tell your neighbor where it is. It's 2 units out on the real axis and 3 units up on the imaginary axis. Then you know it's not up until Friday, that's when you see it. But you might as well indicate it like this: 13 squared.
56.3 degrees.
So this is just another way of writing the same complex number. And this is called polar form. That's all there is to it. It's polar, I get it. So when dealing with polar form, you indicate how far out the number is. That means the radius of the circle that contains the number, if it has its center at the origin of the circle. And then you specify some angle. There are countless angles to choose from, but you must choose one. You specify one of the angles that tells how much the connecting line has rotated away from the positive part of the real axis. and it has rotated 56.3 degrees away. But it would be just as correct to give 56.3 plus 360 degrees. It's just another way to say the same thing. You've just taken an unnecessary step before you start measuring the angle. Are there any questions about that, Christian?
Yes.
You're also welcome to go the other way first, yeah.
And then go up if you feel like it.
Any questions? Otherwise, let's see what happens if I need to find an argument. And I'm not in the first quadrant, but in the second, then the third, and then the fourth, just to see what the cases are.
That's take 4.
And before we do it with the second and third and fourth quadrants, let's discuss something called the principal argument for a complex number.
The principal
Argument. So what does that mean? Well, if I now have here the Gaussian plane, and here is some set of complex numbers, and here is the line from theoretical to C.
So it's a given argument.
It's one argument for the set of complex numbers, and it is written that theta is some argument for the set of complex numbers. But if you choose one particular argument, where the angle is between minus 180 degrees, plus 180 degrees, you always start here. All angles are measured on the positive real axis. Why? Someone decided so. So there's nothing to understand, only to accept. This here is 10 degrees. This here is not 10 degrees. You always start over here. 10 degrees minus 5 degrees. So you always start here. So what does minus 180 degrees look like?
Great.
What does plus 180 degrees look like? If bar.
That was it.
So you can see that from minus 180 degrees to plus 180 degrees, there's a full rotation. So it covers all imaginable angles. So all imaginable angles are covered by the range from minus 180 to plus 180. And you can write it like this.
minus 180.
Which is not included. And I don't know if you remember the meaning of these interval brackets, but when an interval bracket turns away from a number, you're not allowed to touch the number. So minus 180 is an illegal angle. In contrast, 180 degrees is a legal angle. So 180 degrees looks like this, and then I know I'm on the negative real axis. Minus 180 degrees would also be in the same place, but you would be repeating a position, which is why minus 180 degrees is excluded, and 180 degrees is included. So all imaginable angles are here. And if you write a big A in the word ARG, which as an abbreviation stands for argument,
If you write a big A, it means you chose to write a big A. An angle ranging from minus 180 to plus 180. Written like this.
so here it says, what is a principal argument? A principal argument for Z is an angle for Z that definitely falls in that angle interval. We call it a principal argument. So we can put this into the box. So let's say there are 30 degrees here. And with a drawing,
Goodbye,
if
everyone.
there are 30 degrees here, is theta then a principal argument? Yes, because don't 30 degrees also fall in the angle range from minus 180 to plus 180? Yes, it does. Because if you draw this as an interval on an axis, here it will be 0.
It'll be 180 degrees. And out here, it'll be minus 180 degrees.
And the 30 degrees are somewhere over here. So it's within this range. So if something is from here to here, We call it an argument of advice. Are there other angles than 30 degrees that point to that set? Yes, there are. 360 degrees plus 30 degrees. How much is that? It's 390 degrees. What does an angle of 390 degrees look like? It looks like this. Do I also have it on the set? Yes, it does. Is it just as good an argument as 30? Yes, it is. But is it a principal argument? No, it is not.
Are you following me on this?
So for something to qualify to be called a principal argument, it has to be within that range. That's just what was decided. You can see that the decision was fair because 0 is right in the middle, and it symmetrically stretches across from 0. You could have gone from 0 to 360 degrees. That was also an option, but that would have favored the positive angles a bit, so that was not chosen. It was said that we like negative angles just as much as positive angles, so we're also right in the middle with our 0 point here, and it extends to both sides. That's precisely how the scalar product is defined in vector weighting. We'll come back to that later. Let's take another example.
Imagine I have a complex number located here.
Let's see
The complex number -5.
So here is the real axis, here is the imaginary axis, and now I have a complex number z located here, and c is -5 plus 0i. If you write it in rectangular form, I go -5 on the x-axis. I don't go up on the y-axis at all, so I end up there.
So you might ask, do we know an angle that points here now?
Yes, we do. We know an angle that points here. This one, for example. 180 degrees points here, but -180 degrees also points here. Is one better than the other? No. Both angles equally help to tell my neighbor where here is. -180 degrees or
Plus 180 degrees.
So -180 degrees is a principal argument for the set. No, it's not, because it was stated up here that we must not use -180 degrees. It is excluded. So even though -180 degrees is a useful argument, it is not a principal argument. You must not use capital A. You must not write capital ARG for Z equals -180 degrees. That doesn't work. It would contradict our decision that you can't call it a principal argument unless it's within that interval. Now, what is the relationship between an arbitrary argument and the principal argument? Well, the relationship is that any arbitrary argument for a set of complex numbers can be found if I have the principal argument for the set. Just add any number of full rotations to the principal argument. So what does this equation say? Let's read it aloud again. If you first found the principal argument for z, you can find all the others that exist. What is multiplying a whole number by a full rotation? So for example, if p was 1, so if you add 360 degrees to the main argument, you get a new argument, but it's not a main one. It's one of the others. And how many of those are there?
Quite a lot, actually. One for each chosen value of p.
And which p's am I allowed to use? I can only use integer values for p. So p should belong to the set of integers. Remember those? 0, plus or minus 1.
Plus or minus 2, plus or minus 3, and so on.
So here it shows that if you've already found the main argument, how do you find all the others? That's how you do it. Are you following this? Okay. So let's see what happens if we're in the second quadrant. So now we draw again the graph paper, and then we draw a set of complex numbers that lie in a quadrant. I'll just come up with a set first. Let's say the set is called
-3 plus 2i.
So I'm cutting everything from K3 to
You're
V.
welcome.
and then I need to go 2 up.
So that means my complex number is here. Got it.
If you draw the line from the origin to Z, it lies here.
So where are the arguments then? Oh yeah, this is an argument. Base.
this angle right here. It's an argument for the set, but I'm also trying to do it like this.
Bye-bye.
It would also be an argument to say I'm going backwards.
And that's just as valid an argument. But then I could ask you, this angle, would it be a main argument for Z?
Present from
You
here.
can clearly see it lies between 0 and 180 degrees. But this angle here is not a primary argument because it's more negative than minus 180 degrees. So it falls outside that range.
But that doesn't make it worse. It's just not a primary argument.
It's just as good at pointing to the set, this angle here. Those angles there. So how could I find this angle here now? This one, it's my
Primary argument and set. Now I could find it.
well, I could just start by finding the one that's in here.
Hey, gosh.
So I just look at this triangle here and say, how far is it from here to here and from here to here? But you have to be careful because the distance from here, we know it's 2, and the distance here is 3.
That's
Bigger.
-3. If you just take, what's that?
So what happens if I take the tangent to -1?
To -3? No, to 2. We're down with that.
-3, because I need to take the resistance negatively divided by most similar. And this distance is 2, so 2 divided by -3. What happens if I do this? Well, at least it happens that I take the tangent to -1 of something negative. And if you take your calculator and set it to calculate in degrees, and then take the tangent to -1 of something negative, try to see what it gives. I can just take mine and do it and read it out loud for you. If I say the tangent of 2 over -3,
Then I get -33.69.
so this, it gives -33.
0.69 approximately. So you think of minus first as something negative, it gives something negative.
But the angle we're looking for here, was it a negative angle? No, it wasn't. It was a positive angle.
So you can see already that there's reason to think together.
So the angle I get there, where does it land on my drawing? It actually lands. That angle there, tangent of minus first to the imaginary part over real part of my complex number Z, it becomes negative. And you find that angle there if you just blindly tap in on a detour. But I'm not interested in this angle here. I'm interested in that angle. So maybe you can figure out what to do. What should I do with that negative number to get that positive number? Plus 180. Because if I take minus 33.69 and add 180 degrees, it goes like this, and then I land where I need to. So first I go through an angle of minus 33.69, then I just add 180 degrees, and then I land properly, right?
Can you see it? So if I say plus 180 degrees here,
I get the main argument, right? So this must equal the main argument, the argument, right? And note that I've written a capital A in arc, because I mean that a capital A represents the main argument. And if we write it more generally, if you're in the second quadrant, what applies then? If you're in the second quadrant, like if you're somewhere over here, then you can always find the main argument for the set like this. You just take the tangent of minus first.
Seriously?
B divided by A?
where B is marked as part of the whole.
And from the real parts, you just add 180 degrees. And that's how you do it if you want the answer in degrees. If you want it in radians, then
Yes,
it's not
don't look.
180 degrees.
Since pi radians is the same as 180 degrees.
So I could just point at that and then write it down.
Goodbye. This is how you do it in the second category. Do you have any questions about it? So what was the trick? We know that if a complex number is in the second quadrant, what then? Then the y coordinate, or the imaginary part, is always positive. The real part is always negative. This means that when you take the tangent to -1 of the opposite over the adjacent, you're taking the tangent to -1 of something negative. It can't be avoided because the denominator will always be negative when you're over here. And when you take the tangent to -1 of something negative, you get something negative. This means that you don't actually get the angle you wanted that lay there. You find the negative angle that corresponds to the complex number being here, but it's not actually there. And you realize this if you draw it. That's why it's a good idea to draw it when you're trying to find those arguments. Then you can see it. Okay, let's try once and see what happens if we are down in the third quadrant and then the fourth quadrant, and then we've analyzed it all. So now you can just sit back and use a formula afterward. But it's always a good idea to actually draw it and think it through yourself. Let's go to board 5. What happens if we place a third square? Again, we just start by drawing the Gauss plane. And this time we probably don't need to do it with numbers. We can just do it generally. We're laying here somewhere because it's the third quadrant. So here's my z. And again, I draw a connecting line up to the origin. And then I could say, I would like an argument for z. Is this an argument for z? Yes, but is it the main argument? No, because when 180 degrees and then next piece of the manual. So this time the main argument is placed here now. So actually, I want to find this one here. Because that angle there,
That's my main argument.
that's what I want to find. And what do I know about this? Well, z can be written in genuine angular form as a plus ib. But when I'm over here in the third quadrant, what do I know about the real part and the imaginary part? They're both less than 0. They're negative, negative, negative. Both of them are. So here's A, here's B, and both A and B are less than 0. That's what means you're in the third quadrant. That's what's true. And what happens if I take the tangent inverse, completely blue, without thinking? Then I just take the tangent inverse, as I usually do, to b divided by a. Well, since both b and a are negative numbers, it's minus divided by minus, which gives plus, and the tangent inverse to something plus, that gives something plus. So that angle that comes out of there, it's a calculation. The angle that comes out of it, where is it? It's here. So this angle here is the tangent of negative 40.
So consider it.
But that's not the one I'm interested in. I'm interested in this one.
But that one is easy to find. Just punch it into the calculator. So how do I get to what I want from what's easy to find? Well, I just start by finding what's easy to find, which isn't what I'm looking for. Then I just subtract 180 degrees. Then I land where I want to be. So if I just calculate that and then subtract 180 degrees, I'm going that way. And then I land here. And then I get a heading. So that's the main argument. And on how do you find that? Well, you take it and calculate it out. The argument minus the first.
Thanks for watching and have a great day.
And then you just subtract 180 degrees. Or pi. You can also calculate radians. And I can show this because it was something I wrote to show where it was. So there's the formula. Let's take the last case, the one where we're in the fourth quadrant, and then we've been through everything. We've thought it all through. But I recommend always thinking it through. I recommend not just diving into the formula, but drawing it out and seeing what it really looks like. That the angle here is minus 152 degrees. Yeah, that looks about right. So in the fourth quadrant, let's start again by drawing the complex plane. And now we've decided that the situation we want to understand is that we're down here in this area. So Z is somewhere around here. And I'm drawing a line from the origin out to Z. And then I could ask, is this an argument for Z?
Well, it wasn't a main argument, but it's an argument.
So it would be fine if I could find this angle here. And the only thing I was looking for was some angle pointing to Z, so that's good enough. But if I'm insisting that it should be the main argument for Z, then it's this one I'm after. So I'd like to know this angle. And you can see on my drawing, it's negative. So in here, this is my main argument. Okay, what else do we know? Well, we know that Z is A plus IB, because that's how they always write. Z directors around their form. And when Z is down in the fourth quadrant, I know that then the real part is positive and the imaginary part is negative. So I can say here that A I know is greater than 0 and B I know is less than 0. And that means if I take the arctan first without thinking too much. So I set the real part and the imaginary part divided by each other. First the imaginary part and then divided by the real part. If I do that, what kind of angle do I get? Well, since one is positive and the other negative, it's arctan of something.
Negative, that gives something. Negative.
And that's exactly what I want to find out. Well then, this is my answer. So this is the main argument from Z. So I don't need to correct anything there. Well, it just applies that we are in fourth grade. If you think it's a bit confusing, it's just because it is. And you're not supposed to try and remember any of these formulas. It's only shown here so that you can see how you think about it yourself. The safest bet is every time you have a task where you need to find an argument,
You draw it and think about it.
that's what we need to learn. So let's work through a couple of tasks on finding the main argument and arguments. And then I'll go around and help you. So if there are no questions about what's just written here, then I'll erase the board and write a few tasks.
What? Whether it should be a minus here?
B is itself negative, so you don't need to. The number B can be both positive and negative, so you shouldn't write minus B, because then you actually make minus B a positive number. Look at my drawing here. A is a positive number, but B out here, whatever B is negative. And because B itself is negative, you don't need to write another
Because
minus.
then it will say B, and then we become positive.
Okay. Board number 6. Let's try to solve some problems to practice a bit. Sorting in groups. We are voting main argument. What are you setting? Z is called
5 plus I. Set on a 3, 2, 1.
The city is called negative A1 plus 2I. Negative 3, negative 2I.
3 take away 2. I'll just take a couple more.
So, Marama, if you want to pause the recording here, we'll sort out that thing with the class before we continue.
All right, we're back at it. And you've been working through these problems. So let's quickly go over them. And I just need to grab a calculator so I can punch in a number as well. And okay, in the first problem, it says 5 plus I. So let's quickly sketch this out. 5 plus I. So we're going to have to cut 5 units along the x-axis and 1 unit up the y-axis, which places my complex number set about here. And the angle I'm looking for is that cute little angle right down there. And that little angle definitely lies between negative 180 and positive 180 degrees. So I can immediately determine the principal argument.
Capital A in arc and Z.
And this right here, this point, gives us the tangent of minus 40 degrees.
So 1 over 5.
If we're talking the opposite category, it must be 1 over 5. And if I type the tangent of negative 1, then 1 over 5 in, I get 1 over 5 there.
It's such a steady job. It says there's a 3 in it. Such a steady job. Task 2. There are 3 of them in it.
And by the way, set equals 3.
So it's so easy that it's difficult. If I draw it,
so there it is.
3 units up.
You mark the axis 1, 2, 3. So let's say it's laid out right there. And then we can see what the angle is. It's 90 degrees. So here, we don't need to calculate at all. Besides, you can't calculate this using tangent because tangent is not defined at 90 degrees. Because cosine of 90 degrees gives 0, and tangent is sine over cosine, and you can't divide by 0. So here we can just directly read the main argument. The principal argument for Z is 90 degrees. Or if you prefer it in radians, pi over 2 radians.
here comes task 3. It says negative 1 plus 2i.
And if I take another, so I'll need to go 1 to the left and 2 up. That means my complex number is located about here in the second quadrant. That's where it's seen. The angle that I want to find, that's the one for your principal argument. And here we can clearly see that the real part is negative and the imaginary part is positive. So if I calculate the tangent of minus 40 degrees, if I calculate the tangent of negative 40 degrees for 2 divided by negative 1, so this will result in something negative. And the tangent of minus 40 to something negative, that yields something negative. But I'm not looking for a negative angle. I need a positive angle. Thus, the angle I find is here. Well, that angle there, that's the tangent of minus 40.
Until negative 2.
And to that, I need to add 180 degrees, I can see. That will give me the correct angle. So if I just add 180 degrees to it right here.
I'll get the main argument and begin. And that makes, if I just do the math, the arctangent of negative 2 plus 1 AC, yeah?
150. Yes, it looks about right because here we have 90 degrees and then I need to move on. It might actually look quite right. 160, 157. Starting task 3.
Task 4. It says 3 minus 2i. Negative 3, negative 2i.
And sketching it widely. Then we notice we need to go 3 left and 2 down. If it's 2 and that's 3, then we're about here. So the angle I'm looking for, that's the angle right now. Then we'd like to have a main argument. So here lies C. And if I say that the tangent of negative 1 is a plane, then I can say that the tangent of negative 1 is a plane. Minus 2 divided by minus 3. The arctangent of negative 1 to negative 2.
Divide that by negative 3, and this will turn out positive. Then raise it to the negative 1/3 power. Because minus, of course, proceeds without subtracting.
33.7. So the angle I found
Is this really the angle we're going for here? So this is a
Thank you.
decay.
Until the first memory. To -2 over -3.
And from that, I need to subtract 180 degrees. So if I just take that and then say copy and then minus 180 degrees, I end up with negative 146.31.
That's what I wanted to say. If I say negative 180 degrees here.
So here is the main argument presented.
And it went minus 146.
Come in 31. And that looks quite correct too, that this angle here, if we start here and go that way, it's a negative angle. And it's an angle that is more negative than minus 90 degrees. So maybe that does look very right. It's really nice to make that drawing and do that reality check. So you can see that it's not totally off. So what do we have next? So we move on to problem 5, which is the same principle. We could quickly mention that if you have a real number on the real axis, the angle has to be 180 degrees, not negative 180 degrees, because that wouldn't be the principal argument. Negative 180 degrees is an argument for this complex number, but it's not the principal argument. And this one here, negative 5i, it's sadly downward, so the argument must be negative 90 degrees. You could also say 270 degrees, but then it just wouldn't be the principal argument.
Your main argument must not exceed 180 degrees.
Do you have any questions about that? Matt? That's because the number 8 is right here, out on the real axis, right? This means that if you need to measure the size of an angle to that number, you could either measure this way and say 180 degrees, or that way and say negative 180 degrees. But negative 180 degrees isn't included in the principal range, so you have to choose 180 degrees if you want to provide a principal argument.
And then there's the 0. Yes, exactly.
So it's becoming clearer and clearer to us that the real numbers are quite special complex numbers, and the imaginary numbers are quite special complex numbers too. The complex plane covers all of them together. And some of them are quite special, specifically all those that fall on this axis and on that axis. Ask Editsen ko yung angle surux. Kasi kapag sa si. Imita yata si number 6. But you can write an angle surux if you wanted. So you can see right away that it's the real number 16, but you could write angle 0 if you want to.
And with that, you'll discover that one can also write like this.
16 times, right? Or still 0. You can write it like that too. Because Euler's number raised to the power of 0 equals 1, and 16 times 1 is still 16. But that's because there's a clever, perhaps professor level way of applying complex numbers using Euler's number. We'll get to that. Okay, let's wipe the board and continue the story about complex numbers in the pro-teacher way. The subscription is now active. So again, we imagine that we're looking at the complex plane, and on it, we've drawn some sort of complex number set. And here's a complete set on display. And so far, we've seen that you can specify it by describing how far out along the real axis and how far up the imaginary axis. So here is the number A, and here is the number B. But you could also indicate how far it is from the origin to the number. That's what we call the modulus set. And similarly, you can specify the angle theta that exists there. And now we can write the complex number like this, as we've already learned, namely A plus I times B.
But one could also write it like this, as the model OC angle symbol.
It's an angle symbol. And so, an angle. And so model UZ is sometimes referred to as R, for the radius of a fitting circle. So you can also look at it this way.
And there are also some people who have come up with the
It
American
was
version.
just like this.
So you can also view it as a pair of ordered numbers, where the first number indicates the radius of the circle on which the number is located. And the next number indicates the angle to which the connecting line has been rotated to reach the number. So all these shapes here, everyone who comes here, that's what we call polariform. And there's one more I want to mention because it's the coolest and the best, the simplest of them all. It looks like this. And it looks completely spooky at first because like, what the heck? Why do y'all pop up in the picture? And what's Euler's number doing there?
We call this notation the moment.
Euler's formula. And it's actually a version of the polar form because what you can directly read from it is the radius which the circle number lies on. And you can read the angle at which the line connecting to the number is turned upwards. This ends up being the most important way to write complex numbers of them all. Oh, come on, let's get to it. What's interesting about this math course, Math 1, if you were to sum up what this entire course is about, it's all about understanding why this ties in with the Simula course. And once we've completely finished the course, that's the very last thing I'll prove. The connection between sine and cosine and the exponential function. It's called Euler's identity. And is widely recognized by many mathematicians as the most beautiful equation of them all. Richard Feynman, who received the Nobel Prize in Physics in 1968, is quoted as saying that it's our Joule, that formula,
Futurist.
like this outwards.
And otherwise, bring up the
Lofty.
whole England angle as we go along.
Are they aligned with this angle?
All systems go.
Maybe like that. That's Euler's formula, and then there's a variation where you utilize this for
Tilt
this
it.
is up. Euler's identity, what it says here. And this is the one that mathematicians call the most beautiful formula in mathematics. The reason we think of it as the most beautiful is because it includes the 5 most important numbers in math.
The number 0 is a pretty important number.
That's where everything begins.
Marker 1 indicates the distance to the first number.
Reading. The number pi tells us about the ratio between the circumference of any circle and its diameter.
Same as before.
It defines how to take a negative square.
Oh, let's get into it. Tell me. For you, how much can the bank take a bite out of you if you go down and agree to take a loan from the bank? So all these important numbers.
You treat her so beautifully.
The other thing is, it's enough to make you cry when you look at it. And we'll prove this and that right up to the very last session, where we'll make the most of everything we've learned.
I can already feel how excited I am.
So a bit more about the learning form. Let's try looking at that drawing one more time and see how we can learn it. So once again, we have the real axis and the imaginary axis.
And a complex number z. And the distance out to z we call r.
And now we've learned when we reviewed what sine and cosine were all about. And not too long ago, but now I might have forgotten it again.
But they've learned that the hypotenuse is always the same.
Longest side in a right angle triangle.
And this right here is one leg, and this is the other leg. And they have
Corn
been
is a
purchased.
hypotenuse that gets
Driven down
scolded.
by certain specific factors.
And this side right here
It
needs to
certainly
be scaled down by a cosine factor. So it becomes r times the cosine.
to the angle theta that lies there.
And how can one remember by oneself that it's cosine? You can throw a mnemonic that rhymes cosine with adjacent. And this right here is the adjacent leg. And this side over here, it's also been made shorter than r. How much shorter has it been made? It's been shortened by a factor of sine. So you can think
Sine
of,
and cosine as some factors.
Good evening.
so you make it smaller by multiplying. Because the largest sine should become 1, and the largest cosine should become 1. And the smallest sine should yield -1, and the smallest cosine should also yield -1. So you can think of sine and cosine as scaling factors that range somewhere between -1 and +1. And so this side is found by downscaling the hypotenuse by a sine factor relative to the angle. And that means that this complex set of numbers, if I write it in the good old-fashioned way, a plus ib, so in pure angular form, now I can tell you what the number a is. It is actually this. Because a is positioned there, it's the corridor's cross point being altered.
So I can write that down here under the R-cost clarification.
How awesome is that? So I'll just copy paste it down here. And now we can see that R is a common factor because it's a factor present on both sides, which is why we call it common, and it can be factored out. So I can write it like this, R times parentheses. Good thinking, eh? It's closer.
Plus I times sine. Siger.
And I better put a circle around that, right? Because it's an important result. This is how one can write a complex sale.
Where R is the modulus and where theta is the argument.
Yes, just a moment. Do you mean it too?
Here you go. And theta is equal to the argument of se.
If we take it on trust, what I've written over here, even though it hasn't been proven yet, if we just believe that it's true, that the cosine of an angle plus I times the sine of the same angle equals Euler's number raised to the power of the imaginary unit times this angle. Now you can see what it's like if I put this right in that spot over there. So you can see how it is. So for now, we can believe, even though it hasn't been proven, that it might be correct to express Z as R.
Gang E-I-E.
Congratulations. And we haven't proven that yet, because it won't be until the very last course that we'll be able to prove it. But for now, we're just taking it at face value. And why do you describe
This
it
way
that
of handling complex numbers is just brilliant.
First off, it's because one can look directly there and see where the number is located. Let's check out a few examples.
So for example,
One example is this. Let's take a look
The
here.
complex number Z1 is called 3.
Gang of monitor lizards numbers.
I am cut it in half.
What is this? A complex number. Yes, this is the complex number that lies at a distance of 3 away from the origin. So it definitely sits on a circle with radius.
I can tell you there's going to be a big turnout there.
Yes, that was courage you said. Show courage.
Then set the answer to radius within the circle that surrounds us today.
And next, I see the symbol theta. That was my argument. It's what comes right after the I. It's pi over 2. And when there's something with pi in your argument, you know that the person who thought of it, they're measuring in radians. And then they've written the degrees. So the next thing I can see is that the angle is pi over 2 radians. So just like that, we can say that r is equal to 3 and theta is equal to pi over 2. And this means that I can draw it. Where it's positioned, that is this complex number. So it's the complex number that's on a circle with a radius of 3 and is rotated to an angle of 90 degrees because that's the same as 90 degrees.
So it goes 1, 2,
Units
3.
move up here. Z1 is down.
So that means this is actually a different way of writing. This number is the same as the number 3i. Can you see that?
We agree, and it's true.
So you just get used to looking at that so-called I-lock number. And in a way, you learn to sort of ignore that it says I-lock number. The only spots your I actually scans for are the number 3 and pi over 2. And the rest becomes something you get accustomed to. And that's really interesting because many mathematicians have said that math is, to a large extent, something you get used to. It's something you learn.
You simply get used to looking at it and scan the two areas where the important stuff is.
And the reason why Euler's formula is so brilliantly smart is that if I come up with a new complex number Z2, it's super easy to multiply. And it's super easy to divide them when they're in that form. Because then we can apply the rules from the laws of exponents. So let's try that on the next board. Here we'll create an example where I'll show you how easy it is to divide complex numbers when they are expressed in Euler's formula.
So let's move on to board 8.
Example 2.
Let's say again that I have a set of complex numbers, number 1, which is called 3 Euler's number raised by half p. So that's what I invented before, the same number as before. And now I'm going to invent one more. Let's say I take a set of complex numbers 2, which is 6 times Euler's number raised to the power of p over 4. And now I'd like to show you how I find Z1 times Z2.
So C1 times Z2.
Well, that would just be 3 times Euler's number.
In the second half,
Multiply this number, which is 6 times Euler's number, raised to the power of pi over 4. And then you just look at it and take all the numbers that appear here at the front, the two numbers 3 and 6, and start by multiplying them.
So that must be 18, because 3 times 6 is 18.
And now we have Euler's number raised to something, multiplied by Euler's number raised to something else. And we've learned that when you have two powers with the same base, and that's what we have here, a power with Euler's number as the base, add the exponents together. And you can do that even if there's something curious up in the exponent. Fortunately, this becomes clear when you start proving things. So this can be written as 18 times Euler's number raised.
ETU p halve.
Plus 15 minutes.
So I need to add the exponents together. See, over there I can put in a common factor. So that's why I can write it as 18 times Euler's number.
Raised to the power of parentheses pi over 2 plus pi over 4.
And then we can convert this into
Quarters. Here's 2 pi quarters plus 1 pi quarter. That's 3 pi quarters. So this can be written as 18. With an I bolt lifted in bay 3 at a quarter past. And that's the result.
And then the brain might just think, oh,
And it was fun.
but you can actually draw it, so you can visualize what happened. Because that complex number was 3 units forward yesterday. And that complex number was 6 spaces ahead yesterday. And notice where the result is. It's 18 spaces ahead from yesterday. So it seems that when you multiply complex numbers, you need to
Some
multiply.
of their big bikes, I think most call them motori. But it sounds funnier to say motor lights.
but that sure makes sense. So when you multiply two complex numbers,
So you multiply. And what has happened? Well, we can see that the angle has become lax. So the angle from this complex number, which was 90 degrees, has been combined with the angle from 90
So that
degrees.
complex part takes about 45 degrees.
So you multiply two complex numbers by multiplying their moduli and adding their arguments. And it becomes crystal clear how it works when I do it with symbols. Because if you have R1 times the exponential of II times theta 1, so when you multiply by R2e, II say 2, it results in R1 times R2 times Euler's number raised to I times T1 plus T2. And here it says, when you multiply two complex numbers, each time their magnitudes are multiplied and their angles are added together.
Discuss together.
And likewise, if one wishes to take a look,
two complex numbers divided by each other.
So the quotient of complex numbers. So you get that. Here is a complex number, R1 times e to the power of theta 1. That was a complex number. And if I multiply it with another complex number, R2e raised to I times T2, so I must say R1 over R2. And I can subtract the two exponents from each other. So I'll take the top exponent and subtract the bottom exponent using a rule of exponents. This gives me Euler's number raised to the power of I times, and I can put I outside the parenthesis. And then I get theta 1 minus theta 2. And if one needs to translate into Danish what it means, to divide two complex numbers, you divide their moduli by each other and subtract their arguments from each other. And as you'll see later, when we get a little better at all this, you can tell that it actually turns into operations in the pattern shifts and stuff like that. Pulling and pushing together. So all operations with complex numbers can be visualized.
Like something that's being stretched or compressed.
And rotated. And suddenly you can actually start to imagine that complex numbers can be used for all sorts of rotating things. Because you can incorporate time into the angle. You end up with a complex number that just whirls around all year long. And where the distance can correspond to an amplitude that can be used to describe current and voltage in electrical engineering, it's super tough. Any questions about this story? If you want to add two complex numbers together or subtract one from the other, it's easier when they're in rectangular form. If you want to multiply or divide two complex numbers, it's easier if they are in Euler's form.
All right. Do we have time for what we're saying now? Yes, we do. Board number 9.
Now you're about to hear about the complex square thread. And it's really important that they get a good grip on it because it includes your oral questions. Look at the exam. So a new subsection for complex numbers is the complex square root. And to start that story, let's begin by taking a look at something we've seen before, I believe. Specifically, this feature called fx.
Align with egg in second -4.
That function there, if you draw the graph of it, you'll get something that looks roughly like this.
All right, if x is now 0,
It says f of 0, that's -4.
So I know if x is 0, then I need to go down to -4 and hit right here. So let's say it's close here.
Should be -4, that's there.
And then we can gradually see as x now grows.
So x in n-4 will also grow. And it grows what we call quadratically, and it becomes a parabola. So the graph is going to look like this.
Imagine it's fixable.
If I had drawn it a little neater than I have, one will be able to see that the distance from Adigard over there is the same as from Adigard over there.
The two cuts, they're called roots.
So everywhere a graph intersects the x-axis, those are called the roots of that function.
So this here is that one and that one there.
It's roots. And you find roots by asking, when do you give 0? If you ask a function, dfx, when do you equal 0? It will answer. That happens at all my roots. So all those x values, where the graph intersects, that's where we find the roots. This means that it corresponds to asking, when does RSI squared -4 equal 0? Just like that with the needle.
And you can solve that equation by adding 4 to both sides of the equation, because then you end up with x squared. Then I write it with 4. Existent. So we're looking for all the x's that, when squared, give 4. And those are the numbers 2 and -2. So here's x equals plus or minus the square root of 4, which is plus or minus 2.
And what does that mean? There are two roots.
And what do we call these two roots? We call them the 2 square roots of the number 4. So the conclusion is that the number 4 is 4.
I have 2 red squares.
The number 4 has 2 square roots.
And the 2 square roots are
Plus
p.
the square root of 4, which is 2, is 1 square root of 4. And the other square root of 4 is the one called the negative square root of 4. That gives -2. So there are exactly 2 real numbers with the property that if you square them, you get 4. And these 2 numbers are called the 2 square roots of 4. Are you with me? The same applies to complex numbers. Every non-zero complex number has exactly 2 square roots. Every non-zero real number has exactly 2 as well. Good job. Even negative numbers have exactly 2 square roots. Now we've started learning about complex numbers. And we'll see if we can figure out how to explain and deduce how one finds those complex square roots. Partly because it's super fun.
But also, just as a little side note, because it comes from your own mouth.
The question for the exam. But first of all, because it's just fun to think about, we ask ourselves this question. And now, for the headline, which I have written, the complex square root. So this was the introduction to the complex square root. It's not complex at all. It was just to introduce the concept of square root. So now we move on to the headline, the complex square root. Imagine that you're asking yourself this question. Does a set of complex numbers exist? If I provide an Austrian complex number, which I will name double, it's some kind of complex number. So I'll just write here what W is, at least what it's not. Because if it's 0, then there's only 1 square root. And I'm interested in the more general case that if W is not 0, then there are always 2 square roots. We also need to come up with a way to write W. And you can choose to either write it in polar form or in rectangular form, because you can write complex numbers in rectangular form, a plus I times b, or in polar form, r times Euler's number raised to the power of theta. And it turns out, in this very problem, it's smartest to consider W as if it's written just like that.
Polar form, with Euler's notation.
So here it states W is a known complex number, which equals a known distance from the origin times Euler's number, raised to the power of the imaginary unit, times some known calculation angle. And imagine as well that this calculating angle, phi, lies within this interval. What do we call the angle if it lies within this interval? The principal argument. So we've chosen a complex number W, and we have decided to describe it in such a way that the angle is the principal argument. Can we always do that? Yes. Remember that from negative pi to pi is a full circle. So every number can always be expressed with its principal argument. That's just what we assume in order to presuppose something. And it's also important to remember that W is known to us. It's not what we're looking for. We're familiar with it. And I'll go through an example later so you can see what we know and what we're trying to find. But W is already known.
So that's not what we're looking for.
So who is it that we're looking for?
We're on the hunt for the number sets that, when squared, give us double V's. And if we can find them, what have we then found?
So we have found the square roots of W.
Are you guys with me on this?
So that number I need to find, it has to be found. We're on the hunt for that.
We're assuming that It can be written like this. We'll write here in Euler's form as some unknown radius over there.
The Ölstallgang took action in England.
Unknown angle. Just to make sure that you're all still with me.
It's a well-known number. So that's W1.
Can tell.
We don't need to look for that one.
We've got it. What we're looking for is Z. And we choose to write Z like this. So who am I really looking for? I'm looking for R. And I'm looking for theta. And if I can find them, then I've found the square roots of W.
So we're looking for
little r.
and we're searching for theta. Let's get started with the search.
Okay, if I choose to write set, then that's how it is. So I just have to put it in its right place there.
So it's going to say what I sound like.
Squared, it should yield what I know well, as if it were here. Yeah. I've written down the same equation again that I began with. I've just inserted my expression for W and my expression for Z. Okay, here I have a product. And when a product is to be placed at the end, each factor has to be placed at the end. So this can be rewritten as R squared times Euler's number raised to the power of E theta.
Hold the speech on that.
On the right side, I haven't done anything, so I'm just copying what I wrote before. It still says big R times Euler's number to the power of I times phi. And I'll just run through this again once I'm done, so you can get it too, even without taking notes. It'll be like I'm preparing for an exam later with dinner. And Euler's number raised to the power of theta squared. Well, we've learned that we just multiply the exponents. It's a power calculation. So therefore, this can be rewritten as R squared times Euler's number raised to 2 theta.
So I've just taken the total up there and multiplied it by my exponent.
On the right side, I haven't done anything. So I'm still just copying what I've already written. And now I stop to think.
What's on the left side? There's a complex number.
What's on the right side? There's the complex number as well. And at times it shows they are the same. So it forces me to start thinking about when two complex numbers are actually the same. But what if it's located in the same spot on the complex plane? Only if two complex numbers are in the same spot on the complex plane, then we're talking about the same number. Because a complex number can be thought of as a single point.
Stayed. Okay.
How far away is this complex number from 0?
How far away is this complex number from the origin? That's what you're learning right now. Because everything that's before the upper part is the modulus. So if this complex number equals that complex number, then I immediately conclude that little r squared must yield big R. Otherwise, it's not possible. The two complex numbers are only identical if they're equally distant from the origin and if they're rotated at the same angle. Are you with me on this? So from this, I conclude there are two equations that apply. There are two things I can conclude must be true at the same time. The value of r squared must equal big R. That's one thing. And who was it that I was looking for? Have we forgotten about it altogether? Our delight. Just what were we looking for? But I can find it now because the small r is a real number that's positive, since it's a distance to infinity. So here I can simply take the square root on both sides, and I've found the small r. Which square root? The good old real square root. Because this is a real number that squared must give another real number, since it's a distance. And distance is always a real number greater than 0. So right here, I can find little r straight away. Little r has to be the positive, good old-fashioned square root given here. Now I've got something else. So what's the other conclusion I can draw? Well, if two complex numbers are to be identical, they must occupy the same position in the complex plane.
So that was
meaning they must have the same distance and the same angle close by.
Multiple of 2 duty.
All I require is that they occupy the same spot. I don't demand they're described by the same angle, only that the angle points to the same place. So that means the angle 2 theta, what should it equal? Phi up to an integral multiple of 2 pi. And this is the most challenging part of this derivation, to fully grasp it. So let me write it down, and then I'll explain it once more. I conclude that this right here is the angle of that complex number, because it comes after the I. And everything that comes after the I is the angle. So 2 theta is the angle of this complex number. And the angle must point to the same spot on the complex plane as that angle does. When does the opportunity for an absolutely necessary run come?
A whole number of times.
Okay, so let me just explain this again, because it's the hardest part of the education. It says that the angle of the complex number, which is over here, should point to the same place in the Argand plane as that angle does. Or as the angle does if you add a full rotation, or as the angle does if you add 2, 3, 1,000 rotations, or subtract 1,000 rotations. So what number can P be for now? All whole numbers. And that's written like this. For now, P can just be any whole number. We're almost done. We've actually found R.
So here we are, happy and content.
We have found honor. But we still need to find theta.
Because we needed to find R and theta. That's what I had written.
We're looking for R and theta.
So let's now try to find that theta which corresponds to having chosen P as 0. Can I just say that P is 0? Yes. Yes, because if P is 0, then it says that 2 theta should equal 5. That works, right? It's one solution.
But it turns out there's one more solution. Just one more.
And everything else is given. So what I can say now is that twice times the theta corresponding to being chosen as 0, it should be equal to phi. So you see, all I did was to substitute 0 for P in the spread. And because I plugged in 0 for the P values, I'm calling the corresponding theta, theta 0. So what does theta 0 become? So Adam's theta is 0. I can simply find by dividing the equation by 2, right? And this, it just cancels out and gives 0, doesn't it? Because it's multiplied by 0. So Arab's theta is it just becomes arm of here. So I can circle this in red because it's an angle that works, this one. And then I can say afterwards, okay, what if I chose P for the next whole number, E min? But then I'll get 2 times theta 1, because now P equals 1, which has to be the same as P plus 1 times 2P. And then I can divide by 2 to find theta 1. So that gives phi over 2. And when I divide this by 2, the 2 cancels out. So it simply gives pi decimeters.
So here's another angle that works.
Soportima hospitaliseros om en säker But it does work. It works too. But as you can see now, it's giving me a solution that I've already found. Let's just try with PLI2. So I'm on board with the idea that if I just write it down exactly as it is, then here was P.
Here's the job. Now P equals 2.
If P equals 2, what does it say then? Then it says 2. If I look up here, it says 2 times theta 2
equals P plus P, which is now 2.
12 o'clock sharp.
I've got that now. If I isolate theta now, what do I get? So I get theta 2.
Anyway, nicely halved. Can you see it? Because if I divide this by 2, then the 1 cancels out completely. And phi over 2 plus 2 pi, it points to a new place I hadn't found before. It's pointing to the same place as phi over 2, which I had already found, because 2 pi is a full circle. And if you add a full circle to something I've already found, surprisingly, you end up in the same place that I've already discovered. So if you think about it, you'll realize that there are no other places in the complex plane that work except those corresponding to that angle and that angle.
For everyone else, it's just repetitions of the two.
What have we then proven? Every complex number that is not 0 has exactly 2 square roots. No more, no less, exactly 2. And what can we say about the two solutions? They are rotated 180 degrees from each other. So if one is located here and the other there, then the second one is right here, rotated 180 degrees. Was it the same with the real numbers? Let's have a look. Yes. If one square root is there, then the other lies turned 180 degrees. So that also held true for the real numbers. But now it applies universally. No matter where we're turned, they're opposite each other on a right angle biquadratic ray. And I'll just show you with an example so you can picture it. But before I do that, so let me just do what I promised. Let me just do it as if I were taking a test in it. So you can lean back and listen to the explanation once more without placing an order. As soon as I walk through this door, knock and greet the examiner. Hi, I'm Jim. I've drawn question 1, which is about complex numbers and the complex unit circle. And you're my teacher and you're my examiner. Hi. Really good. I'd like to talk about the complex square root. So the story starts over here, and I'm so lucky that it's all written on the board, but that's not how it is during the exam, but it is now. I like to talk about the concept of complex square roots, so let me introduce the notion of roots and square roots. For that, I look at the function f of x equals x squared minus 4. Its graph becomes a parabola with its vertex at 0, minus 4. If someone asks where this graph intersects the x-axis, they're essentially asking to find the roots. We call the roots the points where a graph crosses the x-axis. So we need to see when x squared minus 4 equals 0. But of course it does when x squared minus 4 itself equals 0, because the function is defined as x squared minus 4. And this equation here, you can solve it by adding 4 to both sides of the equal sign. So it'll read that x squared should equal 4. So I'm looking for all the numbers that when squared give 4. And I already know that the answers are 2 and negative 2, because 2 squared is 4. And negative 2 times negative 2 also equals 4. So there are two solutions. They are here, plus and minus 2, corresponding to this x value and this x value. So these are the two roots for this function, and precisely because it's called squaring, and because you find the area of a square by squaring the side length, we call them square roots. So what it means is that the number 4 listed there has 2 square roots. One is called plus square root of 4, which is 2, and the other is called minus square root of 4, which is negative 2. And what I said there, it turns out to be generally true as well when it comes to complex numbers. Every complex number, which is not 0, that is, all numbers in the entire plane, except the origin, has exactly 2 square roots. And I would like to demonstrate this as true and find them at the same time. And so I'd like to solve the equation where a complex number squared, one that I don't know, equals w. And w is a complex number I do know. That's my assumption. But I also assume that it isn't the complex number 0, because then it would only have 1 square root. And I want to demonstrate that it's true. If it's not 0, it then has 2 square roots. I'm also assuming that the known number I have is written in Euler's form, with a known modulus and a known argument. And the last assumption I make is that the argument is a principal argument, which is what I've written down here. I've chosen to denote it as a principal argument, I assume. The reason I assume that is because I can make some general comments about those square wires. So given I know this, C is unknown, so I want to find Z, and I'm writing C down.
Excited as RA in theta.
So what I'm looking for, because I'm looking for Z, is precisely that modulus and that argument, so that the number squared will yield W. That's what I'm after. And if I can manage to find them, then I've found the square roots of W. So now I begin by substituting the expression for Z into its place there, so that Z squared should equal W. I'm going to take advantage of the fact that each factor needs to be squared. So R squared and I times theta need to be squared. And that gives me something that can be rewritten as this. So this needs to be equal to that. And then I pause and think, well, this is a complex number, where this is the modulus, and that up there is the argument. Because this is a complex number where this is the modulus, and where this up here is the argument. And these two complex numbers can only be equal to each other if they have the same modulus. They must match up. And if the arguments are the same up to an integral multiple of 2pi, because the two arguments must point to the same place on the complex plane. And this means the equation gives rise to two equations. The first equation states that little r squared should yield big R, but that must mean little r is the positive square root of big R. And that square root is the good old-fashioned real square root that we learned in elementary school. And what I can also say is that 2 plus or minus a whole multiple of 2p. That means, in Danish terms, plus or minus a whole number of wrong turns.
And that is number p.
It can only be chosen from the integers because it has to be the entire revolution. And then I can just start trying to find all the roots that work. The first root I find is the one corresponding to choosing p as the integer 0. So here it says, now I have chosen p to be 0 because p equals 0 is an integer. So that means 2 times theta 0 needs to equal phi, because that term disappears when I multiply by 0 at p's position there. Well, I've just found an angle simply by dividing this line by 2. So theta 0 equals phi over 2 works. That's an angle that corresponds to a square root. And what's the conclusion if we look at this physically? When you take the square root of a complex number, you essentially halve the angle to it. That means if a complex number is at a 45-degree angle, then the square root of that number will be at a 22.5-degree angle, simply put.
The one angle, the 1 degree.
That's what it says here. So one can visualize it for ourselves and geometrically once one has understood it. So I'm trying to set p equal to 1, as it's one of the other complex numbers here. And if p equals 1, then we just have 2pi here times 1. That's 2pi. Now it says that 2 times theta 1 should equal phi plus 2pi. And by dividing that line by 2, I get that theta 1 becomes phi over 2 plus an additional pe. So it means that if I need to square a number that's at a 45-degree angle, one answer would be at 22.5 degrees, and the other would be at 22.5 degrees, plus an additional 180 degrees.
And now we see that there are at least those 2 square wires.
It ensures that there aren't any others that are different from the 2, because if I choose the next integer PD2, so I get a repeat of the one that belonged to PD0. Because if p equals 2, then it's 2 times 2pi and 2 times theta 2. So when I isolate theta 2, it yields f half plus 2pi. But this is exactly the same spot as the f half square root. So it's not a new square root, it's the same one again. And you'll find that out depending on which p value you pick, whether you choose -1 for p, -2 for p, or 10 for p, you'll end up repeating the 2 roots we found. So there are no others. There are only 2 square roots. One has that angle, the other has that angle, and they both have the same magnitude.
That was the story.
And the complex square root. So just to finish off with a drawing.
If you have a complex number that lies here, and let's say the radius is 9,
and the angle is 45 degrees. Can I then immediately draw the 2 square roots instead? So I just need to take the square root of 9, which is 3, and then the answers are on a circle with a radius of 3. Here's a circle with a radius of 3, as I imagine it now. Where's one of the square roots then? At half the angle of 45 degrees. That is, at 22.5 degrees. That's where one square root lies. And where's the other square root? Rotated 180 degrees. So it's directly opposite. That's where it is. So this is my complex number w. And here is one square root of w. And over here is the other square root of w. I think it's time for a short break. Or maybe any questions? Yes, ask. A question you might get about that would indeed be just that. Can you draw it? And I might also say to you, okay, can you tell me if w lies here? And there's a distance of 25 up to there. So where are the 2 square roots of w located? Then you say, well, the angle is 90 degrees. I need to halve it. So I know that one of my square roots lies on that angle bisector line. And the square root of 25, that's 5. So I have to go out 5 from there. Let's say it's here. That's one square root.
So that's plus the square root of w.
So where does the other square root lie? It's over here because you have to rotate 180 degrees, also known as pi radians.
And that is called the negative square under W.
Okay, let's take a 10-minute break and then we'll continue. Now it's up to you guys to handle some tasks when I finish. So let's make the final push. This will be our last short recording session before we're done for today. Let's try and see an example of how to use what I've just demonstrated here with numbers. So we're still on fading the complex square roots. And that's chalked up as 10.
So here comes an example.
I just call it example 1.
I've got
a
a cop.
complex W.
And that was what was known. I don't need to
It's
look
just
for
something
that.
I'm coming up with now that we all know so well.
After that, it's called 16,
The hallway. And otherwise, speak in an uplifting
multiplied
manner.
by 5.
That's my experience.
I'd like to find the 2 square roots of W.
So how do I know there are 2? I can see that right away because this complex number is not 0. Since W is not 0, it implies that there are exactly 2 square roots of W. And how was it that I found it? Well, I needed to find C, and there was R times E raised to the power of E theta. So let me start by finding R. And here we saw that R was just the good old-fashioned positive square root. What was R set to? And the big R is 16, it's right there. So this is the big R. And phi is pi over 2, right? So I just take the good old-fashioned square root, 16. That's 4. Now I know how far away from the origin my square roots are. They are 4 units away. 4 away from, yeah. And afterwards, I can find theta 0. I don't know if you can remember, but it was just 4.5. So that's really easy. Because that is phi standing there. P is P halve. So I just say pi over 2. And I need to divide that by 2. And you don't divide the fraction by a number every time in the denominator. So this can be written as 10/4 because 2 times 2 is obviously 4.
So one of the square wires is rotated by 45 degrees.
It's 95, so that's 45 degrees. And what about the other one? Well, I find that by choosing the integer 1 for p in that formula, I derived. So it's pi over 2 plus p. And I've calculated that pi halves are pi quarters. So I just need to figure out what pi quarters are. That was pi over 4. But what we know is pi can be expressed as 4 pi quarters, and 4 pi quarters plus 1 more pi quarter equals 5 pi quarters.
So this is a quarter to 5.
But is it a main argument? It's not. Winter is fine. It's just not a main argument. Let's just draw this so we can see what I mean. So if I want to designate it as a main argument, then I can't use that length because it's greater than 10. It's slightly larger than pi because 4 pi quarters make pi. So 5 pi quarters are a bit larger.
Now we can draw it. Let's start with drawing a W.
W leads on a circle with a radius of 16.
So let's just say this is core.
So somewhere on this circle here, so
Here's my W, and it's turned up at an angle of pi over 2, which is 90 degrees. So my W is right here. This is the thing with W. Got it? Do you agree with me on that? And the distance here is 16. From there to there. That's the radius. And now I've figured out that my square wire lies on a circle with a radius of 4. So I need to half it and half it again. That was one halving. That was two halvings. So you have to take a circle that looks about like this. So now I know that my square root lies on that circle. And what I also know is that the angle up to W, which was 90 degrees, needs to be halved, and then I'm on my square Y. So along this bisecting line, one square fits right here, and it turns out that the other square also lies on this line. So where does this line intersect the circle? We cut there, so that's where one of the squares is situated. So here lies, now I just have to go to W. And this can be written as the number 4 times Euler's number raised to the power of I times pi over 4. So I've used that R value, which was 4, and I've used that theta 0 value, which was pi over 4. So I get the one square that lies there. By the way, this is called the principal square. All the square roots that lie over here in a D quadrant, they're called principal. Okay, principal. And this right here, this is the main thing. What's to be gotten out of it? Is the door gone? And the other one, you simply find it by rotating 180 degrees. Just stand here and then rotate 180
That was
degrees,
pretty wild.
and you'll end up right there. Imagine that this square root is represented by a rod that's hinged at the origin like this. Then you just rotate it, and you end up right there. So this is the negative version of the principal square root of W. So if I need to write this down, then I'll just write it under W. Element 4, Euler's number raised to the power of I in the fourth quarter. And minus the square root of W is equal to 4 times Euler's number, times I squared. What was it then? I got 5 picoseconds per quart. So here they are in 2 square roots. And what I hope you guys find cool is that if you've really understood it, you can draw it even before you've done any calculations. And I'm putting more emphasis on you understanding the geometry, even if you can't get the numbers right when you're put on the spot during an exam, because it's always hard to calculate under pressure. Everyone struggles doing math when they're stressed. You know, drawing it is simply the path straight to the halfway point when it's on the other side. So that's the important part. In the real world, it's absolutely useless. But on the other hand, it's fun. Complex numbers can be used for all sorts of things in the real world. But this complex square root, I've never encountered it in a practical problem myself. So why do we learn about it? Because it's such a textbook example of how to understand complex numbers on a deeper level by understanding the square root. In fact, you can think of it as operations in the plane, and it can be used for all sorts of things. And I believe, if I ask ChatGPT, can you give me an example of a practical application for a complex square root? It'll probably come up with something. It's just something I'm not familiar with. Maybe you guys should try asking around about it so I can answer next time.
Andre, trust me.
The short answer is probably no, but I've been tinkering a lot. I've messed around with ChatGPT quite a bit, and it's exceptionally good at math and physics. About a year ago, I caught it making a calculation error with a factor of 2, which I explained to it, and it apologized, and it hasn't made that mistake since. But since then, I haven't caught it making any calculation errors that I've noticed, and its capabilities are just skyrocketing. I mean, it's evolving really fast, and it keeps getting better. So if you dismissed it a year ago, you should definitely give it another look now. And if you dismiss it today, you should check again in 5 minutes, because it's advancing so fast with the new stuff it's doing. It's not exactly developing closely, is it? All right. Any other questions about this complex quadratic thread here? If not, there's one last twist I'd like to tell you about. Anything else? chosen the principal argument. So if you wanted to present it as a principal argument, you'd have to figure out the size of the angle here. So what I've written here can also be written like this. And then let's just think for a moment. If up to here is a quarter pi, and here we have 4 pi over 4, so then this is 5 pi over 4, so we must have 2 pi minus, no, it must be 5 pi over 4 minus 2 pi, because I need to have something negative here, and 5 pi over 4 minus 2 pi, let's work that out. I'll rewrite it in quarters. So 5 pi quarters minus 8 pi quarters. That makes negative 3 pi over 4. So this can also be written as 4 times e.
Una 1. Negative 3 pi over 4.
And this is written with the main argument.
And it was quite funny that you just asked about the plus minus, because that was exactly the last bit I wanted to cover about the complex square. So if there are no more questions, I'm about to wrap up, and then we'll probably get to today's final board. Translated from the assignments I'm just making up. I'll give you a complete answer to your question, Soren, about whether I believe in ChatGPT. I think one should be most careful with ChatGPT.
CBT, if it's about attitudes.
Not when it comes to scientific and accepted facts. And mathematics is probably the safest thing we have. That's where you're most likely to get an unbiased answer, if it's about mathematics. This is also true for Wikipedia and other platforms. If it's about something that's completely neutral, then the likelihood that it's not biased is greatest. And on Wikipedia, there are very few errors when it comes to mathematics and physics. It's truly an ingenious source. But when it comes to politics and that sort of thing, you might need to be a bit more cautious. I don't know much about that myself, but I'd imagine that's where you'd have to be more careful. If it's about politics or religious matters and stuff like that, okay.
So we're just about finished.
To find the square root, w is, and w equals some number r times e to the power of I at some angle beta. And if that angle happens to be a principal value, then it ranges from minus pi to pi. We've just seen that the two square roots of w can be written like this. One of them turned out to be the square root of r, where this represents the entirely ordinary real square root. This is a complex square root sign. You just can't tell by looking at it. You have to know, because the inside is complex. Multiplying and raising to the power of I. We squared it. That was the individual work. And then we saw that the other square used to find the square root of w, it turns out to be the square root of r multiplied by e raised to the power of I times, and then you say phi over 2 plus pi more. So those are the two square roots. And here, I'd like to add a little final twist to that story. Let's now imagine that we have a complex number. It's just some complex number, so it's just z. And that z is raised to some angle theta. So we've seen that it can be written as, see you later. But it can also be written as a plus I times b. We also saw a little while ago that it could be written as r times the cosine of the angle.
Plus e times the sine of the angle.
And we've been a bit tired
That
there.
one was tougher. Santer. Oh,
So it could be fun to see what happens if you lie down. If we add pi to the angle here, then we end up over here. So I've added p plus p. What complex number do I get then? I definitely don't get z. I get a new z. I could call it z prime, a new z, right? The new z I get must still be at the same distance. So I just say cosine of theta plus p. Addition DMC plus p solve for p. So what do we get if we add pi to the cosine of that angle? Let's think about that by drawing some unit circles. So if we have the unit circle here, and here I have the angle theta. So where's the cosine of theta located? Oh, right. It's right there. So this right here is the cosine of theta. You remember this from high school, right? So this is the x coordinate of a point on the unit circle, right? But what if I add pi to it? So I end up over here with my point. And what does the cosine of that angle become then? Which is theta plus pi. It lies here now. Can you see that? So it's just as far, but with the sign reversed. So instead of saying cosine of theta plus pi, I might as well just say cosine of theta, but I need to remember to include the sign. So this can be written as r times negative cosine theta. I drop the pi, but remember the sign. And what about sine? That's this angle. Where does it lie? It lies right here. And see, when we add pi, it ends up here, just as far away. But the sign has also changed. So that means I can write negative I sine. That's it. And now you can see that there's a minus both here and there. So we can factor it out. And it moves all the way to the front of the r. So we're left with cost plus I synth inside here. But what is this number? Oh, that's the number that used to be called z, right there.
So it just shows a minus. It just shows -7, you know?
So the new set has exactly the opposite sign as the old set if you add I to the angle. Can you see that? So that means what is written here is simply adding pi to the angle. Do you see that? So this would be exactly equal to that if you just remember to change the sign, and that's also what's written here, plus minus. So once you've discovered one square root, you've immediately found the other one as well. You just have to remember to change the sign on both the real and imaginary parts. And what does that correspond to? A rotation of 180 degrees or pi radians. So it turns out perfectly. It'll be 11:50. So I guess that's your cue to leave for today. Or I'm not sure if you're heading home. But at least it's lunchtime. And then I'll write some tasks for next time. Thanks for today.
Shut up.
Right during the break, I'll turn it on once I've written down the assignments.
Yes, I will do that.